Okay, I think I'm recording now. Okay, so we'll see. Okay, so before I start, is there any questions? Or is there any issue with the I guess there's no questions. Okay, so let's just give it a shot. This given a lot of series of lectures using iPad and when abroad, but I haven't done things in Taiwan on this. So let me see if it works. Actually, why can't I see? Okay. Okay. Okay, so today we're going to talk about rotating solutions. So we're going to talk about rotating black hole solutions. Okay, so previously we've already introduced, for the last few lectures, we've introduced the short shell solution and the Rising-Northam solution, which is associated when you have both gravity as well as Maxwell fields, and then the solution will be charged. So today we're going to talk about rotating solution, which are more closely related to the real black holes that we have. Now, since we're talking about rotation, so basically you have a notion that you have some object that is rotating, right? So since it's rotating, therefore that means that the metric solution that you're looking for is not going to be spherically symmetric, right? Because you have a particular rotation axis. So that means that there should be some non-trivial theta dependence with your metric. And so therefore that means that the general solution that you will want to write down is for the metric will be something like this. So of course you're going to have the time component, but now the time component, instead of just a function of r, you're going to have dependent on theta. Okay, and of course, similar thing for the radial direction, where you're going to have dependent on theta as well. And now, since you're expecting that the thing is rotating, since you expect that this is rotating, that means that the phi direction, which is in this, so if we have this plane here, and then we know that this is the phi direction, that means that the phi direction should have some kind of time dependence. So you'll expect that there's some time dependence here. What that translates to when you're writing your metric ansatz is that you expect that you're going to have some mixing between the time direction and the phi direction. Okay, so this is basically the hallmark that you're rotating. Okay, and therefore, if you have a notion of how this object, you have a notion of the angular momentum of this object, then this information should be encoded in this function here. Okay, and of course we have the usual theta and phi dependence, but the point is that now the theta square and the phi square, they're not sharing. These two things here, they're not sharing the same function anymore because you're breaking spherical symmetry, right? So you expect that you're going to have these two terms and they don't share the same function. So let me just write down, just put some, so let's say we have some r theta and some j function r theta. Okay. So this will be, if I'm looking for some spherically rotating object, then this will be the ansatz that you're writing down. And so you can see that there's, and now that you guys had actually went back and tried to solve the short shell solution and talk about how the solution is exact, after you have that experience, you can imagine that trying to find a solution with this many of unfixed functions is very complicated. It's a very complicated detail, and that's why, well, that's partially why that the solution was actually given by Kerr. So this is a famous Kerr solution. It was given in 1963. Okay, so so of course we're just writing down the ansatz, and as you guys know, then you need to plug it into the Einstein equation, and you need to solve the differential equations and find the solution for your ansatz. And as it turns out that the solution takes this form. So this is the famous Kerr solution. So we're just going to explicitly write it down. If you want to have fun, you can plug this solution into the Einstein equation to check that it is actually a solution. But as I gradually write down the solution, you'll see that this is actually a very complicated thing. So I'm going to spare you that homework. Don't worry. Right. So we're going to have. So you see that now you have the non-trivial dt d phi mixing term here. I'm gonna write down what rho means in a second. Okay. Plus rho square r square plus a square minus 2m r. So while I'm writing this out, just keep in mind that this is actually the solution that would describe most of the black holes in the sky, because most of them are carrying angular momentum. So even though the Schwarzschild solution is the most famous solution people are familiar with, it's actually this solution that is more relevant to black hole physics. And then this is the sine theta d phi squared. Okay, so there's a few things that we need to write down. So first of all, this r squared is just r squared plus a squared cos theta. And importantly, this solution. So this solution is characterized by two constants. One is of course our m. So one is m, the other is a. Okay. So previously, so the Kerr solution is basically a two-parameter family solution. So the Kerr is a two-parameter family. It has m and a. Schwarzschild, it just have m. And of course, last time we have the Reiser-Nordstrom, and it just have the function. It had two parameters, m and q. Okay. So A is related to the angular momentum divided by m. Okay, so A is basically, and you can see why. So remember, why did we identify this m as the mass? It was because you can expand your solution as r goes to infinity, right? And as you expand r to go infinity, the leading term has an remember that it has an r over gm, and that tells you to identify this m as the mass that you would see at asymptotic infinity. So here this is the same thing. As I mentioned that you can identify that this is angular momentum by looking at the cross term here. And so there will be a homework where I will guide you guys. So basically the point is to identify why this A here is actually related to the angular momentum. So of course at asymptotic infinity, this piece behaves as just basically R over 4AM. Okay. So this is telling you this cross term here. So this is telling you that this A is related to the angular momentum of this object. Okay, good. So notice one thing is, so let's study the solution a little bit. For this, first of all, you'll notice that this function here is no longer the inverse of this function here, right? And you guys were in your homework. You guys were supposed to prove the uniqueness of the Schwarzschild solution, and there you found that these functions should be inverse proportional of each other. But of course, we know why this is no longer the case. It's because of the general ansatz that you start with. The general ansatz that you start with is now different. You're not starting with a spherical symmetric ansatz. And in fact, the Kerr solution is not the unique solution for rotating metric. Okay, so unlike Schwarzschild, so basically, if you have a non-rotating object, if you're very far away if you're very far away, then in principle, a black hole solution looks exactly like a non-black hole solution, because because if you're far away, you have no idea what the mass distribution is, right? So if you don't know what the mass distribution, you don't know if the mass distribution is bigger than the short shell radius or smaller than the short shell radius. Therefore, you can't, just from the solution alone, you cannot tell whether or not it's a black hole. However, here, the Kerr solution is going to be different than other solutions, and I'll send there's actually a large class of different solutions which all gives rotating solution, which all gives rotating a rotating metric. So I'll send you some supplementary material, some papers. If you guys are interested, you guys can take a look at the metric there, and there is no longer Kerr metric. Okay, so so in a sense, in one sense, there's no unique solution for a rotating metric. For a rotating black hole, the solution is unique. So that means a priori, so this is a very important point. So that means that even asymptotically at r goes to infinity, if the object is rotating, you can at least start to tell whether the rotating object is coming from a Kerr solution or is it coming from something else. Okay, so in other words, if the object is spinning, even asymptotically far away, you can actually start to tell whether or not it's a black hole or not. So this is one of the important points that are distinct from short shell, a non-spinning object to a spinning object. For a non-spinning object, as you're asymptotically far away, you can't really tell whether the object is a black hole or not if you don't know the mass distribution. However, here, because of the fact that the rotating metric is not unique, asymptotically far away, you can actually start to discuss whether or not the object is given by a Kerr solution or not. Okay. So does everyone? Yes, actually, this is one of the difficult point about teaching it like this, is that I cannot see the confused face of yours. Does everyone follow? Okay. Let me see if there's any. Yes, there's actually 3 comments in the chat. Let me see. Why without the theta term, dt theta term? Well, because we're so. Oh, okay. So someone already answered. Okay, sorry. Thanks. Okay. Great. Of course, we know that. Of course, then we know that there must be some black hole that can carry both m, a, the rotating, and q. And this will be, and indeed there is a solution, and I'll send you the supplementary material. But basically, this is called the Kerr-Newman black hole. Okay, so this is basically a black hole that carries both charge as well as angular momentum. And so, as I often stress, you can see that indeed that all of these black hole solutions are just classified by just a few quantum numbers, just the spin, the charge, and the mass. Okay, good. So since we have different functions here and here, so when we're talking about horizons, then it becomes more interesting. First of all, just like the case of the usual case of the Horizon Northern black hole, where last time we talked about that there's actually 2 horizons. Here you also have 2 horizons, but you actually have more. You actually have 4 horizons because these 2 functions are actually different. So let's take a look. So first of all, from the dr square, so from the function in front of the dr square. So let's just isolate. So the function in front of dr square. So this takes the form of rho square over r square plus a square minus 2mr. So this function of course has a singularity when r square plus a square minus 2mr is equal to 0. This is the solution, right? So that means that actually, can someone? I think there's some background. If you're not going to speak, can you mute your mic? Okay, thanks a lot. Thanks a lot. Yeah, actually, it's just a lot of people. Are, okay, I'm gonna mute you guys. Okay, so don't worry. If you need to, if you want to speak, you can just unmute yourself. But otherwise your mic is going to be mute. Okay, good. So since the singularity occurs at this point, therefore this tells us that that R the horizon here is given by so let's see. So the horizon is going to by 2m plus minus square root 4m squared minus 4a squared, right? Divided by 2, which of course tells you that this is just given by m plus minus square root, or let me just pull this out. So let me just pull this out. This is 1 minus a squared over m squared. Okay, so basically this gives you, so once again, you see that there's actually an outer horizon, an r plus and an r minus. Okay. Now for the extremal case, so of course that means that sorry, before going to extremal, so that means that in order for this to even have, in order for you to even have a horizon, your a squared over m squared must be smaller or equal to 1. Okay, so that means that the angular momentum is bounded by m squared. Okay, so the angular momentum is bounded by, or the angular momentum or all right, let me just use this. Sorry, since a is not precisely the angular momentum, so remember that a equals to j over m, and therefore it's really that this value is bounded by 1. Actually, let me just check. Right. Okay. So a squared over m squared is bounded by 1, which tells you that for a given mass, there's an upper limit. There's an upper limit for the angular momentum of the black hole, or for the angular momentum. If we require that the horizon must exist. Okay. Because if it exceeds this bound, then that means that this value here becomes imaginary, right? And therefore you don't really have a horizon. So, or to set it another way, is that this function, if you plot out this function as a function of r, then it's going to be it never has any zeros. Okay, then if I call this g of r, and then I plot as a function of r, then if this becomes bigger than 1, then there's no 0, and there's no horizon. Okay, so if we require that horizon must exist, if we require horizon that must exist, then that means that you should observe that this is always smaller than or equal to 1. Okay, and when a squared over m squared is actually equals to 1, then that corresponds to what we call so when a squared is equal to 1, this equal sign, this is what we call extremal black holes. And as I mentioned, in fact, there's many black holes that we observe are actually near extremal. So let me just give you 2 of them. So I'll give you, this is also will be in but of course, what can I give you? I cannot give you a picture, right? So I'm going to give you the names of the black hole in the sky. So, and their A values normalized by M. So for example, I just look through some catalog. I'll send you the reference. For example, this has an A. So this is normalized by 1. Of course, these measurements are derived by fitting with models. So there's a various model fitting, and therefore the value of these are always in terms of some upper or lower limits. So this gives them, they have a precise lower limit. So this is in 2014, they found this black hole, and this has a limit of around 0.983. Here, this is normalized by M. So this is actually a normalized A. There's many of these. I just pick up another one. This has a value of A is 0.98. Okay. So you see that indeed that these are, first of all, these the interesting aspects of extremal black holes. This is not just a theoretical interest. These are objects that actually exist in the sky. Okay, this is the first thing. These are very close to 1. So these are near, at least near extremal. And the second thing is that indeed, so here remember that we were saying that you cannot overspin, and you cannot overspin is because of the fact that you need a horizon. You must have a horizon. And this simple argument actually matches with observation, right? We don't observe anything with A bigger than 1. Okay. And so if you think about it more, if the black hole cannot overspin, it has a maximal value, then that means that as long as the black hole lives sufficient amount of time, then the fact that you can actually observe these near extremal black hole is not too surprising, right? Because it keeps absorbing stuff. So it keeps absorbing angular momentum. So it keeps increasing the angular momentum. And so as time goes sufficient long time, it's natural for us to expect that eventually we'll see many of these near extremal black holes. Okay. However, once again, if you want a theoretical argument for why these things cannot be it's bounded from above, is because then you must have a horizon. Okay. In other words, you cannot have a naked singularity, as we mentioned last time. Okay, but of course, as we mentioned, that this is the function in front of FR squared. There's actually the function in front of dr squared. The function in front of dt squared is different, as we're seeing, right? So the function in front of dt squared, so dt squared is multiplied by 1 minus 2mr rho squared. Okay, where again rho squared is basically r squared plus a squared times cos squared theta. Okay, so so that means that here you have another horizon. So let me write the previous horizon. R plus minus is associated with m plus minus square root m squared minus a squared. Here, this guy is I mean, you can just multiply this rho square over here, just multiply overall rho square, and you see that here, let me call it r, let me call it h plus minus. This is just different by this factor of m squared minus a squared times cos. Okay. So so for a rotating black hole, you actually have 4 surfaces. Now this surface is going to match with this surface when theta equals to 0 and pi, right? And 0 and pi, these 2 surfaces are going to match. So basically the picture that you have is that you have so let's draw a picture. So basically the picture you have is you have the inner horizon. This is r plus. You have the, sorry, this is inner. So this is r minus. So this is r minus. And you have the outer horizon. This is so bad. Oh, I think I can. Yeah, let me remember. And then this will become a square. Yes, okay, this will become, okay. So this is the, but now it's not concentric. All right, this is r plus. All right, so we have the outer horizon. And then we also have, but now we have these RH plus and minus. So RH plus is going to be bigger than R plus. So I'm going to use another color. So RH plus is going to be bigger than R plus, but it's going to match R plus at theta and phi. Theta equals 0 and pi. So then there's this outer horizon here. Sorry, not outer, but this RH plus here. So let me call this RH plus. And then there's, of course, RH minus, which will be smaller than the inner horizon. And therefore, it's going to be something that looks a little bit like this. Okay. Okay. So for rotating objects, so this is for, once again, this is for a rotating black hole. You actually have four different surfaces. The area inside here, so we're going to talk about these areas in detail more once we discuss about the causality situation, the geodesic around these areas. So this is called the ergosphere. And basically here, light ray is going to be trapped. Rays are going to be trapped inside this. This is like a trapping surface. So we'll discuss more about why these are trapping. Okay. Okay. So this is basically the structure that you have for a rotating black hole. Now that we have the structure, of course, now you can go back and plug in the solution. First of all, you can see whether or not the solution actually satisfy the Einstein equation. And then you can also try to plug in the solution into the Riemann tensor. You can plug it into the Riemann tensor and compute the Riemann tensor square and verify that for all of these solutions, there's actually no singularities. Okay, so you can compute this, and you'll find that at the, for example, at the horizons, there's actually no singularity at all. Okay, so since there's no singularity, therefore the space-time is actually smooth. So once again, if you locally go, you're sitting at the horizons, then there's actually nothing happening locally. You only realize that there's something happening when you look at the global structure. Okay, so do we have any questions? Okay, great. Good. So now let's talk a little. So now that we've talked about these solutions, now let's talk about the case when these solutions become extremal. Okay. So let's talk about extremal black holes. Because extremal black holes are interesting, both theoretically and observational. As I mentioned before, that many of these black holes are actually extremos. Now, once again, so basically you can characterize for extremal black holes, you can characterize by the requirement that the inner horizon is equal to the outer horizon. So let's look at the Reisner-Nordström black hole. So once again, the Reisner-Nordström black hole. If you remember that the function that we have in the denominator of the dr square was 1 minus 2 mg r plus q square g r square, where this q square is the charge of the black hole. And therefore, this tells you that the horizon r plus minus that we discussed in our last class is basically mg plus minus mg square root 1 minus q over m. So this tells you that q over m must be smaller or equal to 1. So a given mass object cannot have overcharge. Okay, and we discussed last time that that means that if you have an extremo, if you're sitting around some extremo black hole where Q over M is equal to 1, then you, for example, electron, which I don't know what the value of the electron is, but the value of the charge versus mass ratio, but this has much greater than 1. Then, for example, if you have an electron and you have an extremo black hole here, the electron cannot fall into the black hole. Okay, it's just because if it falls into the black hole, that means Q over M is going to be bigger than 1, and then this violates the extremal bound. So therefore, this will not fall. And then indeed, as we discussed last time, this will not fall because the electromagnetic repulsion, even when you're far away, you get the electromagnetic repulsion is going to override the gravitational pull of these two objects. Okay, good. So just by this I'm going to use this very simple example and explain to you why as a pure Einstein. So the Einstein's theory of square root GR minus 1/4 F squared. So the Einstein-Maxwell. So this is of course the Einstein-Maxwell theory. So basically this is not consistent quantum mechanically. Okay, we can just use this. There's various ways. So as most of you heard, and we'll also discuss this from various different directions throughout this course. But you can also often hear that just the pure Einstein theory with just square root GR minus just the pure two derivative part, R has two derivatives. So just the two derivative part of the Einstein theory is just not consistent quantum mechanically. There's various different ways to see this, and already we can see it here from the very fact that that extremal black hole actually exists. So to understand why this is inconsistent, just think about, let's say we have a black hole, and most of you know that if we have black hole and then we talk about quantum mechanics, then the first thing you know is that since the black hole has an event horizon, let's say R plus, that means that quantum mechanically, since we already shown last time that around the horizon, this is basically just flat space around the horizon. Last time, so you know that there's actually nothing going. You can set up you can sit at the horizon and you can just read your quantum your quantum field theory textbook. And if you read your quantum field theory text, so you know that you can have particle pair production, right? You can produce E plus E minus, for example, because it's flat, so there's nothing going on there. So you, in principle, you should have E plus E minus, and therefore at the horizon, you can if you have pair production, then one of these particles is going to fall into the horizon, and the other particle is going to come out, right? And you can have a bunch of pair production around the horizon. If you have a bunch of pair production, and therefore the picture that you see from the very fact that quantum mechanics tells you that particle can be pair produced is the fact that once you have a black hole, it will start to radiate, right? And this is the famous Hawking radiation. Okay, so you can have Hawking radiation. Okay, good. So that means that at the end of the day, at sufficient long time, the black hole should radiate. And if we're talking about just pure gravity, then you just have gravity and perhaps the Maxwell field and no matter field, nothing else. If we talk about this theory, then you just have a black hole, and then you have a black hole solution, and it can radiate, and it should just completely evaporate. Or it can have that if it's a single black hole, it evaporates, or if it's or it can decay into two black holes or more. Let's say it decays to two black holes. Then let me call this Q. The original charged black hole is Q. Let me call this Q1 and Q2. Okay, the decay end product, because we're just talking about pure Einstein gravity, right? So that means the only objects in the theory is just black holes. You don't have anything else. right? Because you don't have any matter fields. You don't have any matter degrees of freedom. So you just have gravity itself. And if you just have gravity itself, then the only states, as I mentioned, is just black hole states. Okay, good. So then you can have this and plus some radiation. Okay, so this will be a general decay process. Good, so let's think about this. So this will have QM M1 and then Q2 M2. Okay, so let's assume that the original black hole, let's say that the original black hole is extremo, which means that big Q is equal to M. Okay, so this is just a simple inequality. What is the inequality? You know that for the decay process to happen, you must have that Q, because Q is a charge, it must be conserved. So that means Q is equal to Q1 plus Q2, right? Okay, for the mass, M has to be bigger or equal to M1 plus M2. Can anybody, so if it's equal, then it probably makes sense, but it can be bigger. Can anybody tell me why can it be bigger?
Radiation.
Exactly, because you have radiation here, right? So radiation tells you that it can be bigger. By the way, the important thing here is that since it's a charged black hole, it cannot just completely radiate away, right? Because there's a charge. The radiation doesn't carry charge, right? So since it's a charged black hole, it cannot just radiate away into vacuum, right? Because it has a charge. So that's why we're talking about decay process, okay? So importantly, we know that black holes must decay. Okay, because if it doesn't decay, then that means that black holes are just isolated stable states, and then there's various problems with quantum mechanics because you have these infinite possible stable states in your quantum mechanics. Then that means your Hilbert space is non-normalizable because you have just infinite number of stable states that doesn't decay, and that will be problematic. So basically, we take that black hole must decay. Then you see the problem. You need to find these solutions. Okay. So let's say we have. Let me just do exercise. So first, I already know that because I'm starting with an extremo, so I have M equals to Q1 plus Q2. So let Q1 be, let's say, a third M, and then Q2 is 2/3 M. Okay. Now M also has to be bigger or equal to M1 and M2, right? So let me write M1 to be M over 2, and M2 equals M over 2. So let's say it's equal with no radiation. So good. So we do this exercise. So what is the new Q1 over M1? So the new Q1 over M1 is, so Q1 is M over 3, M1 is M over 2. So that's 2/3. That's great. But now you see the problem, right? So the new Q2 over M2 is going to be 3 over 2 M divided by M over 2, which of course is 3/4. So can someone tell me what is the problem with this guy?
It exceeds the bound of extremo black hole.
Exactly.
One.
Exactly. This exceeds the extremo black hole. So this state cannot exist. Okay, this cannot exist as a black hole state. Okay. So maybe you say, oh, but this is just because I've solved it very badly. So let's try something else. Maybe you can try Q1 equals to, let's make the charge distribution a little bit more dramatic. So let's say this is 1/10 of the original Q, which is, the original Q is M. And Q2 is then 10/9 of the original M. But then you see exactly the same thing, right? So then the Q1 over M1 is going to be, this is 1/5, which is great, but then Q2 over M2 is going to be 9/5, right? So you see that as you make the decay end product, the charge mismatch, as you make it become bigger, actually you have the more you get of exceeding the extremal bound. You might think that maybe it's the mass problem. Why can we actually tune the mass to avoid this? So you can change the mass. So let's say we don't have it to be, so let's have it to be m/4 and then m/4. So actually half of the mass of the black hole is given away from radiation. If that's the case, then once again you have Q1 over M1, which is great, which is 5/2. But then you exactly see what the problem is. But then Q2 over M2 is now going to be 5/18, right? So this is much greater than 1. Okay, so this tells you a very important. In fact, you guys can go back and check more. You can assume that there's not just 2 states. There's, for example, you can say, oh, can I try Q3 plus Q4? You have 4 end objects, and then you just try to solve this inequality. Actually, I'm going to give this as a big bonus point to, and so I want you guys to, for those who I'll send it out as an email, but for those who can prove that by solving this inequality, you will always find a particular Qi over Mi bigger than 1 by solving this inequality for any Q or M distribution to satisfy this inequality. You always have this condition. You guys can try to go back and try to prove this. Okay, but you see that there's a problem with gravity now, because first of all, we know that extremal black hole exists, but just by the fact that charge conservation and energy conservation, we know that in order for black holes in order for just a pure quantum gravity, pure gravity theory to decay, to even thermodynamically, for the decay to be possible, you must have stuff that has Q over M bigger than 1, which does not exist in just pure gravity. Okay, and therefore this tells you that basically that Einstein plus Maxwell theory is quantum mechanically incomplete. Just by looking at this is, I guess, so since even though in principle GR classes we're supposed to just talk about classical GR, but yeah, we can talk about it a little bit since most of you already learned a little bit about quantum physics. So you see that immediately you know that you see that there's something wrong with this picture. Okay, the fact that first you know that it must be able to decay, and there's good arguments that that black hole must be able to continue to decay. Then the problem becomes that the extremal black holes, you find that it cannot be decayed because the decay process must require things that are beyond extremal. Of course, in our universe, this is not a problem because we always have a bunch of charged particles that have Q over M bigger than 1. As I mentioned, the electron has Q over M that is much greater, the magnitudes of order greater than 1. So it's no problem for our universe for a charged black hole to decay. But I'm talking about if we just from a theoretical viewpoint, if we just have Einstein and Maxwell as a pure theory, then this theory is quantum mechanically not consistent. Okay, and there's actually very interesting questions that you can pose. So of course we don't believe that Einstein plus Maxwell is inconsistent. So many of the people who are working in quantum gravity are trying to understand what does the fact that Einstein, if you just have pure Einstein and Maxwell theory, it requires states where have Q over M bigger than 1. Then for whatever quantum gravity theory that you have, you must be able to produce these states. Okay, and this has a very interesting interesting discussion. So remember that in the beginning of our lecture, we said that we really have the Lagrangian that we were sitting, we have is the square root GR when we have Einstein-Maxwell 1/f squared. And then in principle, we could have had all sorts of correction terms. We could have r squared, r cubed. We could have f squared, f to the fourth. We could have, for example, f squared r, and so on and so forth. With all of these with unfixed coefficients, right? This is we discussed in the beginning of the class that these are all unfixed coefficients, and so basically, going beyond Einstein gravity, the question becomes what is the principle that fixes these coefficients, right? So if you have a quantum gravity theory, then what the quantum gravity theory should tell us what these coefficients are, right? This is just like, as I mentioned before, you start with Newtonian potential. You know that as you go to high velocity, there's going to be corrections out of the form p squared over m squared corrections. And so you can write down arbitrary p squared over m squared, and then you can do two things. One, okay, I'll discuss that again. So one is that, so remember that we start with V over R, and we know that the Newtonian mechanics tells us this is G big M small m, but then we know that this can be corrected by 1 plus a bunch of p squared over m squared, where in a non-relativistic limit, this thing is extremely smaller than 1, so we cannot measure it. But we know that these effects can exist, and of course, there's two ways of doing this. We can do more measurement and get precise number here, or we can have a new principle where the new principle will guide us to what are these numbers are. Then of course we know what the new principle is. The new principle is relativity, and relativity will tell us what is the completion is, which we discussed in the class. And now we have similar problems here, is that we only know that the leading term, which is what Einstein gave us, the Einstein-Hilbert action, as well as the Maxwell term. Now we know that we can add all of these corrections. And a fundamental question is how do these coefficients, or what are the new principles that guides these coefficients? And one of these principles now is precisely the issue about that black hole must decay. So there's someone who's asking that she's still confused about why it is inconsistent with quantum mechanics. So let me just explain the argument again. And so if you're still confused or you have a precise question, please unmute and ask the question directly. So remember, so let's start again. So we know that there's Hawking radiation, and therefore the black hole will decay into vacuum in the end. Okay, so this is the famous Hawking radiation. So basically, we will have that the black hole, in general, black holes must decay. So if a black hole does not decay, that means it's completely stable. That means that this is a remnant. Sometimes we call remnant. And we generally believe that remnant don't exist. The reason that remnant don't exist is because if remnant exists, that means you have these stable particles that never decay. That never decay. That means that whenever you're talking about quantum mechanics in your Hilbert space, these are supposed to be states in your Hilbert space now, right? Because they're stable states, they're always there, right? And remember that these are Q over M are equal, if you have some remnants where Q over M is equal to 1, then there's infinite number of these states. Right, so whenever you're doing a Hilbert space, you're doing a Hilbert state discussion. There's infinite number of states in your Hilbert states, in your Hilbert states, which you must sum over, and therefore the Hilbert's, in other words, your vacuum carries all these states, to put it simply. Okay, and therefore the sum over the Hilbert space will not converge. Okay, so basically we assume we take as an operation principle that these states cannot exist. They must always decay. Okay, so if you accept that the black hole must decay, then you have that for a charged black hole, it cannot decay through Hawking radiation alone, because the charged black hole must have the charged black hole has charge, so it cannot just decay through radiation. So that means that it can only decay to charge object, through charge object, as well as Hawking radiation. Now, if it's decaying to charge objects and Hawking radiation, And if you only have if you only have Einstein-Maxwell theory, then these charge over mass, these can only be black holes, right? Because you don't have any matter. So that means these Q over M states are only black holes. Then just by this simple analysis, you see that if this decay process is to happen, then your Q over M, you must result in something that has Q over M bigger than 1. But already we know that in Einstein-Maxwell theory, you have an extremal bound for your charge. So that means your Q over M cannot be bigger than 1. So there's a violation. So you run into a violation. In order for black hole, so either you give up that black hole must decay, you must somehow allow remnant, which you cannot do in a quantum mechanic theory, or that you accept that the Einstein-Maxwell theory is incomplete and you need to add more stuff here that allows you to have Q over M bigger than 1. Does that answer your question? No, I guess it was Senda that was asking. Is that okay?
Okay.
Okay, good. So that means, if we assume that black hole must decay, if we accept that the black holes must decay, that means this gives you a principle now. This gives you that any quantum mechanic extension of Einstein plus Maxwell theory must be such that this will allow new objects where Q over M is bigger than 1. Okay, so this is one of the forefronts of current research, and this comes under the name of what is called the weak gravity conjecture. So this is the famous weak gravity conjecture. I'll explain why gravity conjecture. I'll explain to you why we call it weak gravity. So the weak gravity conjecture states that for any quantum gravities theory, the important thing is there must exist a state with Q over M bigger than 1. That's the statement. Okay, there must exist a state with Q over M bigger than 1. And of course, we've seen that this is just because we're requiring that extremal black holes can decay. Okay, the reason this is called the weak gravity conjecture is it's a conjecture in the sense that we don't know exactly, that this is just a statement. We don't know actually how this new state comes about. It depends on what theory you're working with. But it's called the weak gravity because if there exists a state where Q over M is bigger than 1, if you think about the Q as the interaction of EM force and the M as the interaction of the gravitational force, then of course that means that the electromagnetic force is bigger than the gravitational force. That's why we call it the weak gravity conjecture. Okay, this is also related for those of you who've taken the quantum field theory class. This is also related to another well-known statement that there is no global symmetry. There is no global symmetry in quantum gravity. Okay, these two statements are completely equivalent. The reason that they're equivalent is that for those of you who've taken the quantum field theory class, you know that the difference between global symmetry and gauge symmetry is just that you have a gauge field and the gauge field has a coupling G, right? Therefore, in other words, for the relation between gauge symmetry and global symmetry is simply that for the gauge symmetry turns back into a global symmetry if the coupling is 0, right? If you tune the coupling to be 0, then the gauge symmetry becomes a global symmetry. Now, since you have something that Q over M is bigger than 1, that means that in quantum gravity theory, you cannot turn the gauge coupling to 0. And therefore, in quantum gravity theory, you cannot have a global symmetry. Okay, and indeed, this is known to be true that for any known solutions to any known construction of quantum gravity, all the global symmetry that you might have is always completely broken. Okay, good. So this is one of the known principle that one has that can govern the corrections here. Okay, so let me just explain this a little bit. So the reason that the fact that you have the weak gravity conjecture, which tells you that you have Q over M is bigger than 1, governs this is because, so let's consider just the next order correction. So let's say you have the Lagrangian, which is just square root GR minus a fourth F squared. All right, so now so after square root GR, so R is 2 derivatives, because if you expand it out in metric, it has a bunch of blah, 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 and it's 2 derivatives in the metric. This is, of course, 2 derivatives here because the field strength is 1 derivative and the square is 2 derivatives. So this is the 2 derivative part of your action. You can do a derivative expansion. So then the next order is a 4 derivative part. And you can have these numbers. So let me call it A. Let me write down some 4 derivative stuff. A squared, B, for example, you can have R mu nu rho sigma, F rho sigma, F mu nu. And you can have, of course, F to the 4. Let me call it C. So this is the 4 derivative term. So let's say we do a derivative expansion and just stop here and truncate here and leave the 6th derivative order. Let's drop the 6th order derivative term. So let's say if you extend your Einstein Hilbert Einstein Maxwell theory to include these 4 derivative terms, then that means, what does that mean? That means that when you're solving for the equation of motions, your equation of motion is going to be modified by these terms, right? If your equations of motions are modified by these terms, that means your black hole solution is also going to be modified by these terms. Okay, so that means that so you can run through this computation, and you'll find that the new extremal black hole, you'll find new extremal black holes, black hole solutions, and generically, these new extremal black hole solution will have Q over M equal to 1 plus these corrections. So this is some function of A, B, C. Okay, so you get deformed. So remember that we must have Q over M bigger than 1. So you can see that you can actually now have Q over M bigger than 1 just by including these corrections. But these corrections must come in such a way that GABC is bigger than 0. This must be absolute positive. And therefore, this gives a prediction for whatever quantum corrections, whatever quantum theory you have, the leading 4 derivative corrections must have ABC in such a way that the correction to the extremal black hole charge to mass ratio is 1 plus GABC, where GABC is bigger than 0. Okay, so this is essentially this is a prediction of quantum gravity, or not of particular quantum gravity model, but the fact that quantum gravity actually exists. This is the prediction. So, for example, for those of you who've heard about string theory as a quantum gravity theory, you can take string theory and you can compute these corrections, and you'll see that actually in string theory, this is indeed bigger than 0, guaranteed in from string theory. Okay, there's various different, and each different string theory always gives GABC to be bigger than 0. Okay, so this is so contrary to the usual state, that what is out there, or some statements that are out there, we actually know a lot about quantum gravity, even though there's different possible models for quantum gravity, but there's precise prediction from quantum gravity that we actually know. And for example, this is a prediction that we know that any corrections that starts to come in must come for consistent quantum gravity theory. These corrections to the extremal charge black hole must be bigger than 0. And that comes from, going back to the very beginning, comes from the fact that the black holes must be able to decay. Okay. Okay, so I think we'll probably, let me just see if the recording actually works. I want to test the system a little bit. So let's basically stop here today. And tomorrow, so now we've discussed various black hole solutions. So tomorrow we're going to zoom in on the black hole solution, and we're going to zoom in near the horizon. Okay, so tomorrow we're going to start with following along the geodesic as something crosses through the horizon and see what happens. And then we'll also discuss, if time permits, we'll also discuss the causality structure after we pass through the horizon. But for the global structure, so this is basically all that I want to talk about for black holes for the global, for the various different solutions. Okay. Okay, great. Thanks a lot. So let me just stop the recording. I'll try to figure out how to. Yeah. I think I'll stop the recording.